In this video, we're going to learn about Fourier Transform and how and when to apply it. We won't go into the details and break down the numerical technique of implementing the Fourier Transform, which is the fast Fourier Transform. You can learn about this on your own. For this topic, we are simply going to introduce you to the basics. You'll then use the FFT function available in both MATLAB and Python in order to solve the machine problem. The machine problem will require you to record your own voice from the very computer you're using now, using just MATLAB and Python. This video will be very brief, and you'll immediately move on to the machine problem, which I hope you will find exciting. A physical process can be described either in the time domain, h of t, or else in the frequency domain, h of f. h of t and h of f are two different representations of the same function. The first is a representation of the function in the time domain, while the second is a representation of the function in the frequency domain. The Fourier transform allows the transformation from the time domain to the frequency domain, as in the first equation, or vice versa from the frequency domain to the time domain. We list down the general properties of the Fourier transform here. Here are some more properties of the Fourier transform. All of these properties are particularly useful when doing frequency analysis. For now, it is important to briefly mention these and introduce them to you. The main goal of this part of the course is to show you the basics of Fourier transform and how it can be used to analyze voice signals. In signal analysis, such as voice signals, you typically use this convolution technique in order to filter out unwanted signals, such as ambient noise. The idea here is to introduce a transfer function, for example, g of f, such that when you multiply with the original function f of f, the unwanted frequencies are removed or filtered out. Then one does an inverse Fourier transform to their product or their convolution, the output of which is the filtered signal. You would also like to determine how signals are related to each other. This is achieved by the correlation function. For example, in voice recognition, autocorrelation will be particularly useful since you want to be able to determine if two sample voices are from the same source. For example, the signal doesn't have to be audio signals. It can be any type of function with an amplitude that is time or space dependent. For example, a digital image is actually composed of millions of individual pixels of colors. Each color can be assigned a certain amplitude, and that amplitude depends on where the pixel is located. Doing a Fourier transform on these pixels will give you the information of their histogram. The histogram can be analyzed for their correlation with another test histogram to determine if the two images are the same or not. In this part of the course, you will learn how to record your voice in MATLAB and Python. This is a process of converting an analog signal such as your voice to a digital signal. The microphone in your laptop converts the sound of your voice into electrical signals. The microphone is a transducer, and the transducers are devices that convert any analog signal into electrical signals. That electrical signal is directed to your computer's processor, which converts the electrical signal to a discrete set of sampling data. There's a rule we use for sampling data, and that is given by the Nyquist critical frequency, as shown. Thus, if you have a sine wave, for example, with a period of 1 second, then delta equals 1 second. The Nyquist critical frequency is then 1/2 Hz or 0.5 Hz. This means that you sample the sine wave at least twice every period. Here's what the minimum sampling rate looks like. The top figure is our sine wave. The next figure is what happens when you sample at the Nyquist sampling frequency. If you time the sampling just right, then you get the correct amplitude of the sine wave. If you don't get the sampling right, then you might sample at the points where the amplitude is not maximum, just like the ones shown in red. In that case, the sine wave is not at all represented. Of course, you may sample with a frequency much higher than the Nyquist sample frequency, as you can see in C. To use the Fourier transform numerically, we use the discrete form of the Fourier transform as shown. Time is divided into sampling intervals or deltas. This delta is a function of the signal that we wish to convert to the frequency domain. The corresponding Fourier transform integral is then converted into discrete form using the following equation. It's actually straightforward to implement this in any programming software. However, the computational requirement is heavy, especially when you're dealing with complicated signals. This is why the fast Fourier transform, or the FFT, was invented and is the method of choice when implementing the discrete Fourier transform, or DFT, numerically. For completion, we present in this slide the inverse DFT. We're not going to use the discrete Fourier transform techniques to implement the Fourier transform numerically. It is actually too cumbersome and takes a long time to do the transform. The fast Fourier transform is the numerical technique used and is much faster to implement. It's the technique used in any program using Fourier transform. In MATLAB and Python, we will be using the command FFT and IFFT to take the Fourier and inverse Fourier transform of a function. That function is your voice. We will first teach you how to record your own voice using MATLAB and Python and analyze that signal. There will be no example exercises for this lesson. Instead, I refer you to the examples for the FFT command in MATLAB and Python. I will also redirect you to the suggested supplementary links for these, as well as other links to help you understand the concept of sampling.